Thanks, Hashim. Welcome, everybody. As Hashim said, we're going to talk a bit about improving the bearing reliability in electric motors. I think most of what we'll cover here will be perhaps consideration of different things that happens in the field and also during rebuilding or repairing. Typically, electric motors you'll find everywhere. In your house, you'll find them. Just about everything that has any type of mechanical movement will be actuated by some sort of an electric motor. It could be in your washing machine, or in the fan in your air conditioner, for example, your power drills, cordless drills. In industry, though, we also find many motors, much larger than what you find in the home, of course. They'll be in conveyor drives, pumps, crushers, just about anything that rotates. And as such, the electric motor there would be more electric motors than any other machine type in the world. So if an electric motor fails or stops, then the machine itself will also stop. And of course, that can cause many issues with downtime, for example. Perhaps a motor driving a pump, which is similar to what we have in the bottom left-hand corner here. If one of those pumps stops, perhaps it's not too much of a major drama. But, there's still costs involved, of course, but as far as production losses go, they might be minimal. However, if we get a motor like this one, which is driving a crusher assembly, if this motor stops, then there could be perhaps losses of $10,000 an hour, perhaps $20,000, $50,000 an hour. If we've got a stoppage for 6 hours, 8 hours, there's massive losses to the company. So electric motors, the reliability is very important. Broadly speaking, electric motors can be separated into two different categories. You've got your general purpose motors, which have standard dimensions, characteristics. They're basically, you can find these in a catalogue. Many manufacturers make interchangeable motors. Then we have our special purpose or special design motors, which are for specific applications. So, for example, it could be traction motors for locos. It could be specific motors that are integrated into, electric cars these days, for example. So they're specifically designed for an application, not general purpose. If we look at companies in general, how many motors are there out there? Well, looking at a large company, for example, there could be anywhere 850 or more electric motors installed. Medium-sized companies, maybe up to 350. Small companies, maybe not 90. So in general, though, medium and large companies, 60 to 65% of those motors are under 10 kilowatts. So they're only fairly small ones. But on average, 43% of electric motors are repaired, and the remaining 57% are replaced by new motors. Motors lower than 10 kilowatts are usually replaced. These days, though, even much larger motors are just being replaced. They're not being repaired. Anything up to, say, 45, 50 kilowatts are commonly replaced these days. So we're living in a more and more a throwaway society. When the repair cost is roughly 60% the price of a new motor, the tendency is to replace it. So, and as Hashim said, 40 to 70% of motor failures are generally related to the bearings, and electric motors account for many stoppages, many reliability incident reports. General maintenance of a motor, and we're talking about just changing bearings, re-greasing, seals, for example. Not talking about electrical reworking, but it may be around 5 to 10% of the purchase cost of a new motor. So relatively cheap just to replace the bearings. However, we still need to have good reliability. So assuming quality bearings are used, how they're installed, how they're handled, lubricated, how the motor's aligned, that has a huge impact on motor reliability. How the motor's installed, how it's also lubricated. So firstly, we have to lubricate from repair point of view, or the OEM has to lubricate correctly. But then when it's in the field, it has to be also continually lubricated. And it has to be lubricated in the correct way, using the correct grease. How it's aligned, how it's maintained. These are all critical to motor's performance and longevity. Let's look at the design requirements. What does a motor designer have to consider when selecting a bearing type, and what type of arrangement? What does a designer have to consider? Firstly, dimensions. The dimensions of the bearings are generally determined by the shaft size, and the shaft size is generally determined by the power output of the motor. So that's the starting point. Now, to determine the shaft size, the designer has to understand what sort of loads are being applied. So all operational loads have to be taken into consideration. So if the motor is being directly coupled, for example, the radial loads acting on the shaft and on the bearings won't be as high as if the motor is being fitted with a 6-groove pulley, for example, with belt loads on it. So the designer has to take into consideration where that motor is going to be used. He has to understand what these loads are, has to consider the weight of any additional additional components. He has to understand the weight of the rotor itself, plus the pulley, plus the coupling, etc., etc. He has to know whether the motor is going to be used vertically. So there's going to be an axial load, for example. Also, there'll be additional forces created when the power is being transmitted. Speed. Speed's important. Influences the bearing, the lubrication life. Higher the speed, generally the higher the temperature will be. The operating temperature is higher, then we have to consider different types of lubrication, both in type and quantity and relubrication intervals based on the operating temperature. The clearance of the bearing has to be selected correctly. Maybe the seal type. The cage design of the bearing can be the speed of the motor, the speed of the bearing can have an effect on the cage design that's chosen. Normally, ball bearings are more suited for high-speed applications than roller bearings. Vertical mounting. The bearings are going to be mounted vertical. Perhaps there has to be a specific bearing type which can take those axial loads. Also, again, lubrication comes into it. How often it's lubricated, for example, what type of grease is used. Environment. If it's a clean environment, happy days. If it's a dirty environment, a wet environment, a dusty environment, certain seal types are required, and again, relubrication might have to take place perhaps more often to compensate for any contamination that might get into the bearings. So let's have a look at typical designs, we have to consider a few things in a motor, like, for example, shaft expansion due to internal temperatures. If we have a motor operating where the internal temperatures are 80 degrees, for example, and an ambient temperature of 30 degrees outside, there's going to be some thermal expansion of the shaft. We'll normally have a locating bearing on the left-hand side here. Now, the locating bearing is held and locked onto the shaft. The inner ring's a tight fit on the shaft. The outer ring sitting in the housing and would normally be axially clamped. So the cover is clamped up against the side face of the outer ring of the bearing, which then holds it up against the internal cover. The non-locating bearing has to be able to move axially both directions to allow for shaft expansion and contraction if shut down. Now, different types of arrangements, which we'll talk about a bit later, but this is actually showing a deep groove ball bearing at this end, and you'll see there's a wave washer sitting here, and this wave washer is allowed to compress. It keeps a small axial preload on the bearing, but as the shaft expands, the wave washer can compress, which then allows the bearing to float in the housing. So what happens if the shaft can't grow in any direction? Then we have issues such as axial preload taking place, and the bearings become loaded in the axial direction. This will cause problems regarding bearing life. The more the load in the bearing, the more the lower the life of the bearing will be. So another motor shown here, this time with a cylindrical roller bearing. So now the locating bearing is the deep groove ball bearing at this end. It's locked in the housing, it can't move, but on the non-locating side, using a cylindrical roller bearing, it allows for the shaft axial movement or displacement to take place internally within the bearing. Okay, so small motors. Typically, we have two deep groove ball bearings. They're typically sealed or shielded with a factory grease fill. They're generally considered to be low maintenance because no relubrication is required. The bearings are designed or selected, in such a way, and the grease inside the bearing is selected so that the bearing will give long life under normal electric motor conditions. So we could be talking 4, 5, 6, 7, 8 years or more. The bearing life is determined essentially by the grease life. Over a period of time, the grease will gradually lose its good lubricating properties, and we'll end up getting a bearing failure of some time. But providing the OEM has selected the bearing and the grease type correctly, and the motor is used in the way it's intended to be used, then the bearing should see a very long life. Looking now at medium-sized motors. Medium-sized motors typically would still be two open ball bearings. This time they're set up in such a way that they can be relubricated on a regular basis. Now, in some cases, we have what's called a grease escape valve, which is a rotating disc internally, sits here, and this rotating disc rotates. The grease comes in through to the back of the bearing. The rotating grease disc picks up the excess grease and throws it outwards out the discharge slot. Technically, these bearings can't be over-greased, providing there's no blockages in the discharge slot. So these bearings, again, depending on the temperatures and speeds, etc., will have to be re-lubricated on a regular interval. Moving now up to large motors. In this case, we generally have heavy loads on the drive side. Typically, it could be from a V-belt drive, for example. Usually, you'll find the drive side bearing is the non-locating bearing, and it will also be a cylindrical roller bearing. Again, these motors are usually installed with grease valves, or at least some way to let excess grease come out, because they will be required to be re-lubricated on a regular basis. We get up to really large motors with very heavy rotors. It might be necessary to have a cylindrical roller bearing at each end. Now, these bearings can't take axial loading, so therefore it's necessary to have a deep groove ball bearing, or perhaps a 4-point angular contact ball bearing, to locate the rotor and take any axial loads. Again, these bearings, because of their size, need to be re-lubricated on a regular intervals. Finally, vertical electric motors. Vertical electric motors, especially larger ones, may have angular contact ball bearings, for example, to carry the axial loading. With a vertical shaft arrangement, quite often the radial loads will be minimal unless the motor is connected to a driving something with a V-belt drive. It's really important with angular contact bearings that they are orientated the correct way. If they're a back-to-back or a face-to-face design, it's important that the bearings during maintenance go back in the same way. They can't be altered. So angular contact bearings, if fitted the wrong way around, will fail very quickly. Okay, so what is causing bearing failures in electric motors? A study done like back in 1990 shows that lubrication was the main issue relating to poor reliability, followed by contamination, alignment, installation, overload, and the environment. And sometimes it can be a combination. Quite often it's perhaps a combination of all these things which cause bearing failures. So if we look at it from what I'd call an inoperation factor, we've got operational factors such as perhaps overloading, basic care, lubrication, unbalance, for example, can all cause issues. Environmental factors such as water, dirt, poor cooling, vibration. Installation factors where we're looking at poor base condition, poor alignment, soft foot, grounding, electrical installation, commissioning. All of these things are classed as in-operation factors. So let's look at lubrication to start off with. How much grease do we put in? I'm not going to talk about oil lubrication here. I think the majority of motors are lubricated by grease. So if we just consider grease at this stage, how much grease do we use? How often should it be put in? What type of grease? Obviously, something like this is indicating insufficient grease. We've got a massive cage failure. We've got a bearing which has failed catastrophically. When we look over here, we can see too much grease. Grease has gotten in, it's filled up the back of the motor, completely filled the windings up. So how much to start off with? Typically, electric motor manufacturers will generally specify how much grease, what type of grease and how often. That information's not available. The SKF rolling bearings catalogue, pages 110 to 127, has a really good chapter there on lubrication. Talks about selecting the correct viscosity, the correct consistencies, how to determine how much and how often. How much is determined by the size of the bearing, how often is determined by speeds, temperatures, environmental conditions, etc. The other thing that can be used is a program that SKF have put together called DialSet. Now, DialSet's an application which is typically used to determine the dial settings on the System 24 automatic lubricator. However, it's a useful tool because down in this area here, it gives you a feed rate in grams of grease per day. It's also available as an app for your phone. So you can very quickly put in the bearing type, the speed, the temperature. We can put in contamination conditions, moisture, for example, whether it's a vertical shaft, whether we're lubricating from the outer ring, whether it's got shock loads, loads are moderate, heavy, medium, etc. And it will automatically calculate down here a feed rate of grease per day, grams per day. The other thing we need to consider, whether you're manually lubricating, whether they're using automatic lubricators, is we need to consider perhaps the cage type. For example, a pressed steel cage in a cylindrical roller requires lubricating more often than a polyamide cage will. Temperature, shaft orientation. Think about, can excess grease exit the seals? If the excess grease can't get out, then it's eventually going to fill up the inside of the motor. Quite often you'll find that the grease ducts that are in the exits from the bearing, they're sometimes blocked off for transport purposes. And they need to be removed first, or else the motor will just fill with grease. What about looking at the loads on the bearings now? As I said, the motor manufacturer selects the bearings based on the typical loads. What if you've got excessive belt loads? Perhaps the drive's been over-designed. Maybe whatever the motor is driving, somebody's decided that we need to put 8 belts, 8 C-section belts on, for example, instead of 5 B-section belts. Straight away, we've got so much more load on the bearing, which is going to cause a couple of issues. One will be reduced bearing life because of the load. The other will be perhaps higher bearing temperatures. Higher bearing temperatures then require adjustments to relubrication. Perhaps we've got a motor with ball bearings in it, both on the drive and non-drive side. Perhaps it's designed for a direct drive and somebody's decided to fit remove the coupling and fit a pulley on there and a belt drive. The ball bearing now is going to be overloaded or excessively loaded compared to what was intended. What about high axial loading? Is there a reason for high axial loading? Perhaps the motor is turned with a vertical shaft and there's extra axial loading on there. What about misaligned shafts? The misaligned shafts between a motor and a pump, motor or gearbox, will add additional load to the bearings. Oops, sorry about this. Okay. What about underloading the bearings? Something that's quite often not considered. If we have a vertical shaft, Perhaps there's no radial load on the bearing now. What about test running after a motor's been put together? In some cases, the mass of the rotor mightn't be enough to put sufficient loading on the bearings. If you've got a motor which is connected with a rigid coupling and it's aligned very accurately, in some cases, that rigid coupling can carry the load of the rotor, and whatever the motor's connected to, the bearings in that can actually be supporting the part of the mass of the rotor, which then unloads the bearing. Let's have a look at an example here. We've got a motor with a fan. The designers put a cylindrical roller bearing at this end to take the mass of the fan, and a deep groove ball bearing on the non-drive end. So looking at the radial loads, we've got a reasonably high radial load acting downwards at the front, and perhaps a vertical upwards load, a smaller one acting on the deep groove ball bearing at the rear of the motor. Look at our axial loads. The ball bearing at this end is not only taking a radial load, it's also stopping the rotor and fan from moving in this direction. So it's carrying the axial load. What happens now? How have the bearing loads changed? Firstly, the axial load. It's increased considerably because now the bearing at the non-drive side has to carry the axial load from the rotor and the mass of the fan. Perhaps that axial load's now too heavy. Perhaps that deep groove ball bearing needs to be replaced with an angular contact ball bearing, for example. How about radial loads? What's happened to radial loads? They've gone to practically zero loads. So now we've got the situation with a cylindrical roller bearing, which might be too lightly loaded. If it's too lightly loaded, then the rollers won't rotate well, and they could end up causing skidding damage. So that's one thing to consider. Misaligned shafts, they'll always cause strain, stresses in the shafts, in the bearings, couplings, in the driven machine and the driving machine. So it's very important to ensure that you've got good alignment. Machine base alignment. What if you've got soft foot? Perhaps you could have angular soft foot, where the base of the machine is on an angle to the mounting surface. Perhaps you've got parallel soft foot, where you've got a gap between one of the feet, for example. What happens if you tighten that up or ignore it? What issues do you have? You could have a weak or damaged or a flexible type sole plate or base plate. You could have, definitely it's going to give you shaft alignment issues, but also there's a possibility of distorting the bore of the end cover of the motor, for example. If the housing bore distorts, then there's a good chance that the outer ring of the bearing will also be distorted. Take care when fitting other components. The face of a coupling does not normally look like this. This was actually one that I saw in the field where the coupling had got stuck halfway on and the fitters proceeded to bash it all the way on with a hammer. They've been hitting it so hard that these pins here wouldn't even fit correctly in the holes. So needless to say, that motor had to be pulled apart again and the bearings replaced, because all that impact damage had been taken by the balls in the locating side bearing. Current leakage. This is becoming more and more prevalent, especially where you've got machines which are operating with variable speed drives. This is where you get electric current passing through the bearings. It's passing from the inner ring through the rolling elements and arcing through the lubricating film, causing damage to the raceways, causing the grease to become hard, drying the lubricant out. It's a fairly large problem, but there are solutions for it. Some of these solutions can be fitting insulated bearings in. SKF do a range of bearings. The larger ones are what's called Insucoat, is a insulating aluminium oxide layer that's plasma coated to the outer surface of the bearing in most cases. In some cases, it can be on the bore of the bearing as well. This doesn't change the dimensions of the bearing, and the bearings can still be fitted in the normal way that any other bearing could be. So that coating helps prevent the current flow through the bearing. With the smaller bearings, we quite often use what's called hybrid bearings. Now, hybrid bearings have your normal steel rings, but the rolling elements are made of bearing grade silicon nitride. And again, that then creates an insulation which blocks the path of the current flowing through the bearing. Dirty environments. Possibility of getting dirt into the bearing, and certainly change to the cooling effectiveness. So if we get the cooling fan slots or the grooves through here full of contamination, we're now not having good cooling effectiveness, which means that the bearings will then be operating at elevated temperatures, which means what? Changes in temperature means the grease might break down, for example. Vibration from other machines during non-operation. So we've got a bank of machines here. One of these could well be a standby machine. It's sitting there stationary. We've got vibration from around here causing the rolling elements in the bearing to be vibrating backwards and forwards, which then causes depressions in the raceways. It's what we call false Fresnelling. So to get around that, we should be rotating machines on a regular basis. Just don't let it sit there for 6 months, 12 months, not operating, because if you do go to use it, if you do need to use it because it's a standby machine, the bearings will normally fail very quickly. They'll be quite noisy. So it's better to rotate the machines on a regular basis, or perhaps there's a way of strapping the shaft or clamping the shaft so that the vibration around doesn't cause the movements to take place within the bearing itself. Now, that's probably covered what I'd call most of the in-operation factors. There could be some others, of course. We need to now look at what I'd call out-of-operation factors. So this deals with improper rebuilding and repair procedures, perhaps the incorrect bearings installed or the incorrect lubricant, and we've also got to consider transport and storage of the motor. Now, bearings are made with extreme precision. You know, if the shaft is out of shape or the housing bore's out of shape, and we fit a precision bearing in there, what's going to change shape? It won't be the shaft and it won't be the bore of the housing. It will more than likely be the inner or outer ring. So they will change shape to suit the shape of the housing or the shaft. So we have to make sure that the the form or the shape is correct, we also have to make sure that the fits are correct. The bearing inner ring should be the correct fit on the shaft to prevent threading corrosion and creep, and the outer ring should also be a correct fit. An excessively loose fit allows relative movement to take place between the inner ring on the shaft. For example, we could get threading corrosion. If the clearance, if the fit's not quite tight enough, we could then get creep. Creep means that the inner ring is rotating relative to the shaft. That then creates wear, which then creates more creep, which creates more wear. We can get small particles wearing from the shaft in the inner ring of the bearing, which then get into the grease and cause wear internally within the bearing. It could lead to heat, smearing, scoring, seizure, ring fracture, etc. If we've got an excessively tight fit, this reduces the clearance, the radial internal clearance in the bearing. If the inner ring's too tight on the shaft or the outer ring's too tight in the housing, we lose the internal clearance in the bearing, which increases operating temperature. Again, if we increase operating temperature, that could have an effect on the lubrication. We also get increased mounting forces. Potentially, if it's too tight, the inner ring could fracture. I'm not going to go into the scope of this short webinar, certainly doesn't go into this, but I do recommend that you have a look at this publication, pages 66, 68. It's got the recommended fits, it's got recommended shaft and housing tolerances for electric motor applications. When you're doing a rebuild or you're changing the bearings, it's important to measure the shaft, to measure the housing bore, record all those dimensions, make sure that the shaft is round, make sure the housing bores are round, make sure the fits are correct. If the bearing is loose on the shaft, or perhaps the fit isn't correct, tight enough, we quite often see what's called threading corrosion. Looking at the bores of these bearings here, you can see this rusty looking appearance. It's from where the inner ring has been moving slightly. There's micro movements occurring, and these micro movements mean that the asperities or the high points, if you like, on the shaft and the bore of the bearing are rubbing together, and these microscopic sized particles break off and they oxidize, causing threading corrosion. My advice is that if you look at a bearing from an electric motor and it has threading corrosion in the bore, there's a good chance that the shaft will not be to the correct size. It will be perhaps, the fit won't be as tight as it should be. On the outer ring, it's quite common to see threading corrosion. Usually we only see small amounts. If we've got large amounts of threading corrosion, it's an indication that the bore could be out of shape, but it's also an indication that there could be a very severe vibration problem. Threading corrosion is caused by vibration. If the fit isn't tight enough, the ring will move slightly due to the vibration. So if you eliminate the vibration, you then will usually eliminate the threading corrosion. But if it's severe, as is shown here, I would be looking at reasons as to why this machine is vibrating so much to cause this severe threading corrosion. Here we see it in the bore of the bearing as well. So we've got a twofold problem here. We've got an issue where the bearing isn't tight enough on the shaft. We've got potentially an out of shape housing here or severe external vibration. Just remember, if you're doing a repair job, don't go getting into this threading corrosion here with emery paper or flap discs. Try and just remove the high points, the rusty components with something like Scotch-Brite pads, etc. Don't remove any material, because if you remove material, you'll make the bearing bore slightly larger, which then increases the fit, so to speak. Ineffective repairs. Gluing the bearing to the shaft is not an effective way to repair it. Side or axial clamping, for example, with a lock nut, will not clamp the inner ring correctly on the bearing. The bearing must be a correct tight fit on the shaft to prevent movement from occurring. Certainly, knurling or peening is not an acceptable way of repairing a shaft. Mounting bearings correctly has to be done correctly. You've got to be using the right tools. Small bearings up to 100 millimeters OD can be fitted cold. The important thing to remember here is if the bearing is an interference fit on the shaft, the fitting tool must apply the force to the inner ring. Likewise, on the outer ring of the bearing, if the bearings are tight fit in the housing, we must apply the fitting force to the outer ring. If you don't do that, the rolling elements being harder than the raceways will put indentations in the bearing, and you'll have a noisy bearing on startup. Preferably, bearings should be heated on the induction heater, for example. Try and achieve a minimum 80 to 90 degree temperature difference between the bearing and the shaft. That's usually hot enough to fit the bearing on the shaft without any issues. A word of warning, try not to use or don't use an infrared temperature type gun for determining the bearing temperature. There's too much issue with emissivity, and you won't record the bearing temperature correctly. It's important that the temperature probe is attached to the inner ring of the bearing. Cylindrical roller bearings, just to avoid damage when fitting, one of the issues with cylindrical roller bearings is that the rolling elements at the 12 o'clock position drop downwards. If you've got the outer ring or the inner ring of the bearings on the shaft, the outer ring of the bearing is in the end cover here. As you're trying to fit the end cover on, the rollers can drop down, and if not done correctly, they'll cause damage to the inner ring of the bearing. For that reason, the suggestion is, firstly, we should be packing the rollers with grease, applying a film of lubricant to the surface of the inner ring. Certainly try and rotate this whilst you're installing it, but more importantly, make up a sleeve, dummy sleeve, which sits on the shaft, a loose fit, and that pushes the rollers up into position whilst you're pushing the end cover on. That will help prevent any damage to the bearings. Radial internal clearance. You've got to make sure that the bearing being fitted has the correct clearance. Most common for electric motors is C3 clearance. In some cases with small motors, they could be less than normal clearance. The reason for that is so that they operate quietly. However, if a motor is designed to have C3 clearance bearings and you fit a normal clearance bearing on, there's a good chance that the clearance will, during operation, will be removed, and you'll end up having a bearing which is running quite hot. Also, factory fill grease. There's many different grease types to suit sealed or shielded bearings. If a bearing is being operated in a motor and the motor is subject to very high ambient temperatures, it's not advisable, or you shouldn't be using a bearing which has normal temperature grease in it. There could be a special high temperature grease that's required for that application. When you're packing grease into greasable bearings, ensure that you've got good clean grease. Make sure you're not mixing grease, changing consistencies, changing grease or oil types. The correct amount of grease is generally pack the bearing, 100% fill, and the housing is filled 30 to 50% to allow for expansion and excess grease. Don't overfill it. Make sure you're using good, clean applicators to fit the grease. Looking at testing a motor, in some cases, the rotor weight will not necessarily give enough load. If you test running a motor without load, there's a possibility of damage to the bearing due to skidding. So in some cases, it might be necessary to make up an attachment or a grid, a jig to apply an external radial load. And finally, transportation and storage. It's a good idea to strap the shaft somehow, whether it's using some type of a strap or a metallic, a metal strap to apply an axial or radial preload to stop any vibration. It's preloading the bearing to stop any vibration from causing false Brinelling. Make sure the motors are stored in a clean, dry and vibration-free environment, and it's good practice to turn shafts every 3 months to ensure that the grease gets distributed around the rolling elements. So finally, excuse me, anything you need to know about bearings and electric motors, there's really good references in that rolling bearings and seals and electric motors and generators publication, as well as the rolling bearings catalogue and online. So if you've got any questions, please, this is the end of the session. Hopefully you've picked up something from it, and more than welcome to accept any questions that you may have.